previous class, actually I have talked about that if I have some kind of physical system, then how to formulate the classical control problem, and after that how much one can talk about the modern control, and then what is main motivation to apply optimal control. Okay, and what we have actually seen that whenever I have multi-input multi-output system, then whatever things we have learned during the classical control course, or if I have nonlinear system, then it is very difficult to apply. Okay, and sometimes it is impossible to apply, and due to that reason we have to explore the modern control engineering or modern control theory. And most of time, if you see the modern control engineering, that is also sometimes people are telling linear control and non-linear control, so that is fully based on the mathematical model. Okay, and we have different courses on the mathematical model. So some system is governed by differential equation and difference equation, some system is governed by the partial differential equation. Okay, and that is called infinite dimensional system. Some system is governed by stochastic differential equation, or some probability concepts are involved. Okay, so for that we have some separate course, but in this course, that is course on optimal control, I am going to concentrate ourselves to those class of system which is actually model using the differential equation. Okay, and deterministic differential equation, we are not going to assume that some unknown things comes into picture. Okay, whenever some uncertainty will come to the system, we are assuming that uncertainty is always bounded. Okay, I don't know the exact evolution of the uncertainty, but I am assuming that uncertainty is not unbounded. So that kind of assumption, that is called robust control, and if you are also going to involve optimality, then robust optimal control problem. Okay, and we have already seen in the previous class that whenever we are formulating optimal control problem, first step to give the clear-cut mathematical description of the process. Okay, and I have taken very simple example that I have some car, and objective is to move on one-dimensional road. Okay, and I have to move, and moving distance I have defined dt, and rate of change of distance we have defined as a position, and rate of change of velocity we have defined as acceleration. Okay, and I have two different command, either I can accelerate and deaccelerate, and for that I have assumed that I have two different way, alpha t and beta t is available to me. Okay, so some kind of circuit or some kind of physical mechanism is available to accelerate something or deaccelerate something. Okay, so this is second order differential equation. Most of time whenever we are model something using higher order differential equation, then some concept, at least the physical interpretation, is very difficult. Why it is difficult? Because suppose I have some quantity x, you can just, in this particular case, you can take xt as a position, then you know that x dot, that is velocity, x double dot, that is acceleration, but I do not know what is x triple dot. One can interpret that is as a jerk, but again if I will ask what is fourth derivative, so somehow physical meaning is lost. Okay, so if you are going to represent any higher order differential equation by set of first order differential equation, then we have clear cut physical meaning. How physical meaning comes into picture? Because whatever variable that is involved in order to represent higher order differential equation using first order, that I am defining as a state. Okay, so in this particular problem you can see that d double dot t, alpha t plus bt is there. So what I am going to do, I am going to take two state variable x1 and x2. X1 I am going to take as a dt, and x dot I am going to take as a d dot t. And after that I am going to represent x1 dot t equal to x2 and x2 dot t equal to u1 plus ut, where u1 is alpha t and ut is beta t. Okay, so anyone has confusion on this representation, then please let me know. Anyone? So here, since in coordinate of x1 and x2, this whole system is represented by first order differential equation. So here you can see that only two things are available. Some quantity like a state x1 and x2 and their derivative rate of change. Okay, so now I have just two things, either quantity and their rate of change. So if I interpret some quantity as a x and their rate of change as a x dot, then I can able to apply same like Newton's law, and we are able to characterize this system. Okay, we are able to define the equilibrium point using Newton's law. So several things I can involve, several classical notion of physics is involved if you are going to represent system using first order differential equation. So after representing the system, what we have to do, we have to see the performance measure. Okay, so whenever we are developing some kind of system, so always developer has some kind of intuition. Okay, they have some kind of objective, and with that objective they want to deliver that kind of product to the market. Okay, so here what is our objective? I want to deliver such kind of car which can actually travel some distance from A to B, that is as fast as possible. Okay, that is our objective. So basically that become the performance measure. But it might possible that some people or some consumer, they want those kind of car which can actually not too much complicated, and using less amount of fuel they can able to run from far distance from A to B. Okay, so at that moment I have different objective function. Okay, and in previous class I have already told you that performance measure is always a scalar, because I can only able to compare the scalar quantity. So whenever we are defining some kind of performance measure, at that time I have to make sure that that quantity should be finally come to the scalar. Okay, now once we define the performance measure, then we are also looking towards the boundary condition and some kind of physical constraint. Okay, boundary condition means here you can see that in second order differential equation, when this system is evolved, at that time I have some information of the position and velocity. Okay, so that is nothing but the state of the system. A state means if I know some quantity, initial quantity, and if I know the mathematical model, then I can talk about the futuristic evolution of the quantity or physical evolution of the variable. Okay, so it means that uniquely I can able to predict the future if I know the initial condition and mathematical model of the system. That is the meaning of a state. Okay, so whenever you are talking about engineering system, at that time differential equation is given and initial condition is given. Okay, and after that I have already told you that whenever we are defining some kind of control, then always I have some kind of objective. So what is my objective? That initial condition, that position is 0 and velocity is 0, and xtf I have to move to xr. And in this process you can see that always I have some kind of physical constraint. What kind of physical constraint? Suppose if I want to accelerate the car, so I have some kind of physical hardware that is involved in that process. So I cannot able to make that acceleration very fast. There always exists some upper limit. And similarly, there always exists some kind of lower limit for the deceleration. And whatever fuel we are going to use, that fuel, so you can see that I have started at T0 and TF. So in this whole journey, some fuel is consumed, and I am assuming that rate of consumption of fuel that is proportional to the acceleration and how fast we are going to move. And due to that reason, this type of expression comes into picture. And G is telling that amount of fuel or gallon of gas or something like that. Okay, so in this way we are also stating the boundary condition. Boundary condition means in order to start the evolution of this particular system, that is required. And after that, this constraint is required in order to meet some kind of physical constraint. Okay, so up to here, anyone has confusion? Anyone? Okay, so now try to understand the analogy between calculus and optimal control problem. Okay, so what is main motive of optimal control problem? The objective is to determine a function that minimizes a specified functional, that is nothing but the performance measure. So here you can see that in J I have defined TF minus T0, and J I have defined TF like this. Okay, so here J, whatever argument of J, that is nothing but some kind of function. Okay, so and what basically we are doing here, I have second order system. So we are mapping from R2 to R or R plus. Okay, why I am telling R plus? Because suppose I just want to compare two things, so it is better that I map everything in some kind of positive real number. Okay, so mapping from Rn to some positive number R. Okay, or you can R. So meaning of functional, whenever we are talking about functional, at that time basically I have some kind of real valued function. Argument might be vector, but whatever resultant, okay, that is some kind of real valued one dimensional quantity. Okay, that is the meaning of functional. Okay, and what is our objective? Objective, I have to define some kind of function. Okay, so here in this particular process, you can see that this G is function of xt and ut. Okay, so what we have to decide? We have to decide admissible trajectory xt, admissible control ut, such that this J has some kind of minimum value or maximum value depending on the our information. Okay, so now could you please tell me the difference between function or functional? Bhavita, could you please tell me the what is difference between function and functional?
Sir, no idea.
Okay, Iram, are you here?
Yes, sir.
So, so are you able to distinguish between difference between function and functional? Okay, Nandita, please go ahead.
Functional means is performance measure. Performance measures.
No, I am just telling that what is difference between function and functional. So performance measure is obviously some kind of functional. Okay, but I want to distinguish between function and functional.
With the help of functional measurement can be done.
So if you see carefully, then whenever we are defining some kind of function, I have some kind of independent variable. Okay, and after that I have certain kind of dependent variable. independent variable is lie in domain space and independent variable is going to lie in range space. Am I right? Anyone has confusion on this? Okay, so whenever we are selecting independent variable, now I can select independent variable, maybe some kind of real number, set of real number or something like that. Okay, but whenever we are defining some kind of functional, at that time, whatever argument, that is function. Okay, so here you can see that whenever I am defining j, at that time, here first I have to know what is xt. So how to define xt? I know the time, evolution of time. So based on that time, I can plot xt. So you can see that that is function. So independent variable is time, and after that I will generate some xt. Okay, so xt becomes some kind of function now, and now using that xt I am going to generate some kind of new quantity. Okay, so now argument of that new quantity is function. Okay, so functional is nothing but function of function. Anyone has confusion on this? Have you understood this point or not, Binay?
Clear, sir.
Okay, so that is the difference. Means argument of functional.
Sir, we can also say that functional is the argument of many function.
Yeah, you can tell. So function of functions means that is many function.
Okay.
Okay, so in this way we are distinguish between function and functional. So here, Babita, now could you please distinguish UT is function or functional?
Sir, UT is function.
Yeah, and now are you able to understand G is function or functional?
And G is the functional.
Yeah, G is the functional. Okay, anyone has confusion on function and functional? Then please let me know. Okay, so functional means most of time what I am doing, I have n-dimensional space. We are mapping to one-dimensional space. Okay, and whenever we are seeing the higher dimensional space, so in higher dimensional space I have function. Okay, and function might be multi-valued. Okay, multi-valued means that xt might belongs to 2 dimension, 3 dimension, n dimension. Ut might be based on requirement, that might be 1 input, 2 input, n input. Okay, but finally I have to map to the some scalar quantity, and due to that reason, in this slide what I am telling, that the next slide I'm going to now I will okay, full screen mode I will keep. Okay, so here you can see that the objective is to determine a function that minimize a specified functional, that is called the performance measure. Okay, try to understand here what in calculus we are doing, that in calculus we are trying to determine a point that yield the minimum value of the function. Okay, whenever we are because we are also talking maxima and minimum of some function. Okay, so at that time we are just searching for some point. Okay, but here what I am going to do, now I am not going to search about some point, I am going to search about some kind of function, whole function. If you see here that x dot equal to f xt and ut and t, and same performance measure I have written, generalized performance measure. Here you can see that I am going to define xt, that is function, ut. Okay, so I am going to search some kind of admissible trajectory, admissible control, such that j has some kind of minimum value or maximum value or extremum value based on the requirement. Anyone has confusion? So now, are you able to understand the difference between calculus problem and optimal control problem? Anchal?
Yes, sir.
Are you able to distinguish? Could you please repeat? What you have understood?
Sir,
What kind of problem we are solving in calculus? Suppose I am going to solve some kind of minimization problem in calculus. What does it mean? Some other people, could you please interpret, Shiv?
Yes, sir. An optimal control problem that minimize the functional, and calculus minimize the function.
Yeah. So what kind of things we are getting during this minimization in calculus and in optimal control? Shiv, could you please answer this question?
So by the calculus, you find a value of some function.
Yeah, point. We are getting some kind of value.
Value,
Okay,
yes,
some specific value we are getting. Okay, same kind of things I have written to determine a point that yield the minimum value of a function. Okay, in optimal control, what basically we are doing, we are trying to find whole function that minimize the functional. Okay, so you can see here that same kind of things I have written in terms of mathematics. Okay, what I am telling, suppose you have certain kind of generalized performance measure. How I have defined, please forget about that for time being. What I am telling, suppose you have this system. Now what you want to do, you want to develop some kind of optimal control such that I can generate optimal trajectory xt. Or what is meaning of generating optimal trajectory? You have to move from one point to another point, okay, in some kind of optimal way. So you know the feasible trajectory or admissible trajectory. Corresponding to that trajectory, you are going to search some kind of admissible control. So that admissible trajectory I have represented by x star, okay, and corresponding to that I have u star, means control action. And what we are telling, that if x star and u star is the optimal one, then now you can select any other combination of xt and ut that is less than, that will satisfy this kind of relation. Then only I can tell that x star and u star that that is optimal in the sense of this performance measure. Okay, have you understood this point or not? Iram, are you able to
Yes, sir.
understand this point?
Yes, sir.
Okay, so in optimal control, I am trying to search some kind of admissible trajectory and admissible control. Okay, now let us come to the next question. Okay, what do you think? Optimal control problem is unique problem, or corresponding to some trajectory x star, unique u star will exist or non-unique u star will exist? Uniqueness, that is unique or non-unique? Or you can just give answer like this. Suppose you know the initial point or final point. Okay, now I have to solve optimization problem or optimal control problem. So how many possible optimal control exist such that they can minimize some kind of performance measure? Is that unique or non-unique? Anyone please answer? From master side, could you please answer this? Master student. Okay, I will call the name. Okay, so Subham, I think Subham, could you please answer? Utkarsh, Subham.
So I think it will be non-unique.
Non-unique. Okay. Shikhar, what do you think?
So non-unique.
Yeah, that is non-unique. Okay, so that is same like, means whenever I have some system, so I have infinite many way to design the control action. Okay, so that is again non-unique. So non-uniqueness is sometime good, sometime sorry, not good also. Okay, so what do you think? What kind of things I have to first confirm? before going to deal with the optimal control problem. But what theoretical things we have to confirm? Anyone? Those who are mature guy in control system, could you please answer? Iram, could you please answer? Because you have already taken one semester course. Or baby Dina? Or Silpi? Anyone, could you please answer?
Sir, the continuity or differentiability.
Suppose I have some system. Now I want to know that some control is feasible or not. So what kind of things or what kind of test we have to perform?
So
The
controllability.
Yeah, controllability. Okay. Meaning of controllability is only that control is feasible or not. Okay. So I want to move from some point to some point. So controllability test we have to perform. Okay. So before solving the optimal control problem, first we have to see the feasibility. But most of time what happens in practical situation, we are not testing that. Okay. Why? For linear system, we have well-defined notion of continuity. But for nonlinear system, most of time we have some notion, obviously, but not so much generalized notion like linear system. Okay, so due to that reason, we are not actually going to see the existence of the control. Somehow we are trying to optimize this function or extimize this function. Okay, but a standard way, first we have to see the possibility is there exists some optimal control or not. And question is very, very simple, that now you know the initial point or final point. So you have to see the controllability with respect to that initial to final point. There is no need to see the controllability of whole space. Okay, because you know that in optimal control, here only I have some kind of feasible trajectory or admissible trajectory is there and admissible control is there. So just we have to see the admissible region, and if in admissible region, that is combination of X star and U star, if that is feasible, then we can define the optimal control. So obviously, if we know the whole space is controllable, it means that I can move from any point to another, any one point to any other point. Then that is more better, because in that way we know that now possibility of existence of optimal control is increased, because I can move from one point to another point. Okay, anyone has confusion? And due to that reason, you have to understand the notion of controllability. And if you see the notion of controllability, you can see that somehow that is very, very inclined towards the optimal control problem. Why? Because whenever we are talking about controllability, at that time we are also specifying the time, in finite time, if it is possible to move from one point to another point. But most of time we are just using a asymptotic controller. But here, whenever we are solving the optimal control problem, you can see here T0 to Tf, I am specifying the time. Obviously, optimal control is also possible if Tf is infinity. Okay, it means that I have improper integral. But most of time, if you see the objective of optimal control problem, that is matching with the definition of controllability. Because in finite time, if we are able to move from one point to another point, then we are telling that system as a controllable. Anyone has confusion on this point? Please recheck the definition of controllability. Obviously, I will revise in this course. Okay, so now at least we are able to understand now that what is relation between calculus and optimal control problem. Okay, so calculus, we are searching some point, some kind of point where I can tell that some function has some kind of minimum or maximum value depending on our requirement. Okay, so now whenever I have function, what basically we are doing, we are taking the differential of function. And how basically we are defining the differential? That is delta f, that is we are taking the increment, and after that we are doing the Taylor series expansion. Okay, and if you see the Taylor series expansion of this function delta f, so that function is basically approximated like this. Okay, so here df by dt, I'm just taking the one dimensional case. So in this figure I'm interpreting everything. You can see that I have t star, and here I have incremented to t plus delta t. So corresponding to that I have some ft star, and after that here I have ft star plus delta t. Okay, and delta f, that is called differential. Okay, so differential is nothing but the difference of these two. Okay, so now are you able to understand the difference between differential and differentiation of some function? From this expression, try to see. Here this is differential and differentiation is involved here. Okay, so this is the relation between differential and differentiation of function. Okay, similarly here you can see that whenever we are talking about the optimal control problem, at that time we are defining some new notion, because here I have to give some different name. Okay, that is same like the calculus, that is called variation. Okay, and what is meaning of variation? Again, here you can see that I am incrementing time, because argument is time, but here argument is function. Okay, and due to that reason I have to take increment inside the function. Okay, so xt is incremented by delta xt. Okay, and I'm assuming that Taylor series expansion should satisfy. For that, continuity requirement is obvious. Okay, so now again you can see here that after doing Taylor series expansion I will get this kind of things. Okay, and interpretation is again like this. So what is main message of this slide? That whenever we are solving calculus problem, at that time we are talking about differential of a function. Whenever we are solving the optimal control problem, at that time we are talking about variation of the function. Okay, and in this way we are defining the differential or variation. Okay, if you check the online lecture, okay, then I have taken some example where I have demonstrated the example of the differential and variation of the function. So please check it. Okay, now let us come to the role of function and functional. So the variation plays the same role in determining optimal value of a functional as the differential does in the finding extremal or optimal value of the function. Okay, so using the help of differential, basically we are talking about maxima and minima. Similarly, using the help of the variation, we are going to talk about the extremum, or you can tell that optimal value of some kind of functional. Okay, so let us first try to understand the calculus problem, and after that we are going to tell same thing for the same kind of things for the optimal control problem. So this is a story about the calculus, that if I know the differential and if that is greater than equal to 0, then f star t is a relative local minimum. Okay, and if this relation will satisfy, then f star t is a relative local maximum. Okay, and necessary condition for optimum, that df equal to 0. Okay, so in this way we are defining the optimum of a function in terms of the differential. Now you can see that whenever I have to solve the optimal control problem, same way, just I will replace differential by variation and I will state the same result. Obviously, I will tell you the proof of this result. Okay, that is called fundamental theorem of calculus of variation. Okay, so that is not recorded. So, but I will tell you the whole proof. Okay, by taking the extra lecture. Okay, or in interaction class I will tell you the proof of this, and proof is very interesting. Why proof is very interesting? in that way, you are able to understand the Lagrangian, you are able to understand the Hamiltonian, both kind of things using same proof. Okay. So now what I am telling, that fundamental theorem of calculus of variation, and based on that one part or almost complete part of control, another part is called dynamic programming. So I am not talking about dynamic programming. So at least half part of optimal control problem is based on this particular theorem, that x star to be a candidate of optimum, the first variation, you can see that just I am talking about first variation, must be 0. Okay. And that is, I have to make sure that I have written first variation like this for all admissible value of delta xt. This is necessary condition. As a sufficient condition, second variation should be greater than 0 for the minimum, or for maximum, second variation should be less than 0. That is the statement of fundamental theorem of calculus. Okay. Whenever you are solving the optimization problem or maximum or minimum minimization problem of function, you know that how one can calculate the maxima and minima. Okay. So same kind of result is extended here. Okay. Those who forget about this, means optimization of function, please again relook the literature. Okay. Now what happens, that I have already told you that whenever we are solving some kind of optimization problem, at that time some constraint might be there. At that time we are modifying the functional. Okay, that kind of things we are going to learn in this course. Okay, so for time being, please do not worry about this part. Just I am telling that all online lectures are available here, so please go through that particular lecture. Okay. So now let us come to the conclusion of the today's lecture. But what we have seen in this lecture, that how problem of calculus and problem of variation is correlated. Okay, what kind of things we are performing in calculus and what kind of different thing we are performing in optimal control. Okay, how to formulate the optimal control problem. Okay, what is fundamental theorem for calculus of variation. Okay, we have also stated without any mathematical proof. So in next class we are going to try to cover the proof. Okay, because we have to state lot of results, so it might possibly within one class, that is not possible. Okay, so now lecture is in from my side. So if you have any confusion, then please let me know. Anyone? So